We begin lecture number 15, and today's lecture we will cover the our introduction or entry into small scale effects in a wireless multipath channel. And this gives us a very interesting insight, also a very rich mathematical framework as we will go through the concepts in detail. Let me begin with a quick overview of what we have mentioned in the last class, and using that as a starting point. In the last class we have talked about the large scale effects and specifically about shadowing. We refer to it as a log normal shadowing, and as I mentioned, that's because in the logarithmic, when you write the equation in the log domain, the variable that we are looking at has got a Gaussian distribution. And so in its normal form it will have a log normal distribution. So the path loss we model as a average value plus a statistical quantity which is Gaussian, or normal with zero mean and variance sigma squared. That tells us that the received signal will actually be the average value minus the random variable, and we related this to outage by saying outage occurs when my received signal is less than a predetermined threshold, which we call as P min, which you then relate to x of sigma, and we relate to the Q function. So the probability of outage can be written as a Q function, and it is one where if we think of it at a certain distance, think of it as an annular region. The Q of beta by gamma tells us what percentage will be in outage. So basically the red shaded regions give us the outage probability. If you want to reduce the outage, you look at the parameter that is defining the amount of the percentage of outage. It's Q of beta by gamma. If you want to reduce that, we have to increase the argument of the Q function, which basically means that I must increase beta. Beta is the margin, or I must reduce the standard deviation of the shadowing. Again, sigma is something that we may not be able to control, so what is in our control is the margin beta. And of course the complement of the outage region is the region that is having a satisfactory signal. Notice I did not say good signal, because all you are asking for is the signal be above the threshold, and therefore that is an acceptable signal. So that was our understanding of the log normal shadowing. We now move into after that we went into the effects of small scale. Small scale as opposed to large scale, we are talking about changes in the signal which happens when you are moving of the order of 10 to 20 lambda. And one of the things that immediately come into play is that there is a Doppler shift of the received signal, of the center frequency of the received signal, depending upon the direction of motion. So for the nth multipath component, assuming that beta n is the angle subtended between the direction of propagation and the direction of motion, the carrier shift can be positive or negative depending upon the angle subtended. We denote it as a carrier, the original carrier minus a shift which is caused by Doppler. So the second component is what is the Doppler component, and again, we normally in digital communications we don't worry too much about the Doppler, but we will see why this is going to be an important component this is the Doppler component. This is the carrier frequency. So in other words, the modulated signal which is centered around a carrier frequency tends to be shifted, and that shift depends upon the velocity with which we are moving and also the angle that is subtended between the two. So given these two parameters, we now recognize that each of the received signals, each of the received multipath components is not exactly at FC, but it is slightly offset to the right or higher or lower depending upon the angle. We then said that we would characterize multipath propagation. Again, I have reused the slide from the last class so that you will be familiar with it. We took the case of a three component system where it was alpha 1, alpha 2, alpha 3. All of them are gains that can vary as a function of time. The delays also can vary depending upon where your position is. Again, this is a model that we are deriving under the assumption of non-line of sight. Basically, none of them are direct line of sight. So this first path you have to take it as a also as a reflected or a diffracted path. So in general, it would be a summation over n, where n goes over the number of multipath components, each of them having a gain alpha n and a delay tau n, and again each of these can vary as a function of time, and S of t is the modulated signal. The point at which we stopped the discussion was we wrote down a general expression for the modulated signal in terms of the information part and the carrier part, wrote it down into the complex baseband and said this is the complex baseband representation. The received signals are going to be the transmitted signals with certain gains, certain delays, and the Doppler shift, all of which we would have to incorporate. So that is where we stop. We pick it up from there and move forward. So any questions on the multipath model? Basically, we have moved over from the large scale effects to the small scale effects. These are effects that will become visible or will start having an impact when we start moving in small perturbations around the current position. So basically the received signal, as we mentioned before, will be represented in this fashion. This is the bandpass signal. The S of t can have a representation in terms of the baseband signal in terms of u of t. And now what we would like to do is write the received signal in terms of the modulated signal, and then get a baseband representation of the signal. So basically I begin with writing down r hat of t. R hat of t, I basically have to substitute the values of S of t into this expression. This is a modulated signal, so I will write it as real part of the summation over n alpha n of t u of t minus tau n of t, right, and e power j 2 pi, no longer only fc, it will be fc minus f Doppler of the nth component t minus tau n of t. This is a representation of my received signal, modulated signal. So what I need to do is if I can isolate the carrier component e power j 2 pi fct, then what is left becomes my complex baseband signal. So my goal is to take out the e power j 2 pi fct, keep the remaining terms, and therefore I can get the representation that we are interested in. So let's write down the expression. So basically I would look at the terms inside the bracket. So the terms inside the bracket is what I am going to simplify. So the terms inside the bracket are alpha n of t. I am going to take u of t minus tau n of t all the way to the right side, followed by e power j 2 pi fct. That's one component, that's what I'm interested in. Everything else has to be included inside as the coefficient of u of t minus tau n t. So this would be e power j 2 pi fc into tau n of t. Let me use a different color. The next term will be e power minus j 2 pi fd comma n t minus tau n of t, okay, and basically I would have to take the summation of these terms and the real part of these terms. That would be my total expression that would be involved. Okay. So I'm going to go to the complex baseband notation. So what remains in the complex baseband notation are the following terms. This will remain, this will remain, this will remain, this will remain. This goes out, so I drop the real part. So the complex baseband representation says R of t, it's a complex valued signal, IQ signal. This would be given by summation n alpha n of t e power, is there a minus sign here? Okay, there is a minus sign, e power minus j 2 pi fc tau n of t e power minus j 2 pi fdn t minus tau n of t times u of t minus tau n of t. May seem a little bit complex, but again it's actually nothing but a magnitude term. This is like, you can think of this as a gain, and this is one phase term, and it is a function of t, and basically there are two things that are coming into play. One is the tau, that is the delay. That's what we saw as the delay coefficient. And then t is a function of time. So there are two variables here which need to be handled carefully. One is delay, the other one is time. And I'm going to emphasize that a lot, very significantly in today. That is going to be one of the key differences in terms of our understanding of the multipath channel that we are working with. So this gain term or this phase term, I'm going to write it as e power j theta n corresponding to the nth multipath component. It's a function of two variables. It is both t and tau. Okay? And the second one is also another phase term. So basically there's a gain term and two phase terms. This will be represented by e power j psi n of t comma tau. Okay? So and of course I can combine all of these and write it in the following form. R of t is summation over n h of n t comma tau u of t minus tau n of t. Okay, so basically h of n corresponds to each of these terms that are there inside the summation. Okay, so basically what we have done is taken the representation of a baseband signal, use the multipath model. So it would have been straightforward except for the fact that there was a shift in the carrier frequency due to the motion of the receiver, and therefore caused a different Doppler shift for each of the multipath components depending upon which direction the multipath component was coming from. So that basically gave us the substituted equation, basically gave us a representation in terms of a gain term which was there in the original equation, plus there are two phase terms. One important point to note is that these phase terms are a function of two variables. One is time, the other one is delay. Now isn't delay also some form of time? The answer is typically yes, but in our context we need to differentiate between the two, and I will explain that a little bit more. So each of these phase terms are a function of t and tau, and so therefore the net result is this expression. Okay, so we refer to this as a time varying response of the channel. So basically it is a time varying response. So this is the received signal through a time varying multipath channel. Time varying multipath channel, and that is what we have represented here in general form. Okay. Any questions about the notation or what we have used here? Okay, now I want you to pay very, very close attention to the following aspects. So basically I want to write down the expression for R of t. R of t we said was summation over n, the multipath components, h of n t. I'm going to represent the output of the multipath channel. So let me take let me come back to this equation. Let me say that at time t equal to t1, there are three distinct multipath components, and the delays of the multipath components are tau1, tau2 and tau3, and they have certain amplitudes. Okay, that's the net resultant amplitude. So basically I would capture that in this equation in the following manner: h of t minus tau n, u of t minus tau n. Okay, maybe but I'm writing it at time t equal to t1. Okay, now there's a very subtle temptation for us to call it the impulse response. Now, impulse response, if you will recall, is defined for what type of systems? Linear time invariant systems. So, impulse response implicitly assumes that it is linear and time invariant. In our case, linearity is guaranteed, but time invariant is not guaranteed because it is a time varying channel. So, basically there is no notion of time invariance, but this does look like a convolution. So, what is actually going on? So, the way we understand it is, we have to differentiate between the time axis and the delay axis. So, if I were to represent the delay axis along the x direction, amplitude along the y direction, and in the z direction, basically going into the plane of the paper, is the time axis. So, these are the axes that we have represented. So, at time t equal to t1, I can tell you what the channel behaves like. It says there are 3 multipath components, one at tau 1, tau 2, tau 3, and the gains are alpha 1, alpha 2, alpha 3. Now, at time t equal to t2, it may be something totally different. It may be just 2 multipath components with the following impulse response. And at time t equal to t3, it could be something totally different. Again, this is because of the time varying nature of the channel. Okay, so now how do we interpret this particular equation? So, what it says is the received signal r of t at time t equal to t1, at time t equal to t1, I'm defining this equation only at time t equal to t1. At time t equal to t1, it has got 3 multipath components with the following delays. So, basically we can write this as alpha 1 e power j phi 1 u of t minus tau 1. That will be one of the components that we would get. Second term would be alpha 2 e power j phi 2 u of t minus tau 2 plus alpha 3 e power j phi 3 u of t minus tau 3. So, it is alpha 1 e power j phi 1 times the signal u of t that was transmitted tau 1 seconds before. Then again a second one, but this one is multiplying the signal that was transmitted tau 2 before, and tau 3. Now, you may say, well, this looks awfully like convolution, but please be careful, because the minute t changes, this equation changes. So, it's not so all we can say is at time t equal to t1, the output looks like a convolution in the tau domain. Okay, in the tau direction, it looks like a convolution, but don't generalize it, because across time it does not hold. So, therefore, this is something that we always visualize the multipath channel in the following way. In terms of a 3D plot. There is the delay dimension, there is the amplitude dimension. Typically for most channels, time invariant channels, that's what you would have. You would have just the time and delay, or both on the same axis. But for us, the time axis has to be different, because the impulse responses are different at the different instances of time. I know that this is probably maybe a new way of looking at it, but this is what I would like you to start thinking about. Anytime you think about a multipath channel, time varying multipath channel, I want you to think about it in this direction, in this way. Any questions? Is the notion that there are 2 different axes, both of which are time in some sense, and both of which have units of seconds, but you have to differentiate the 2, because that is what is the nature of the channel that we are dealing with. Okay?
Sir,
yeah.
So, the time axis denotes the transmission time or something?
You can think of time axis as the actual physical time, basically like the clock. Time, t1, t1 plus 1, t1 plus 2, like that. Basically, it's the clock that is moving forward. At each clock instant, you can take a snapshot of the channel and you get some kind of an impulse response. So that is what we are working with. Okay, and typically you may not want, it's actually a continuously varying channel, right? But we may interested only in discrete time instances when we observe the channel. So again, we have discretized the channel. So the time axis is continuous. The delay axis can also be continuous. So in principle, what you would have to define a multipath time varying channel would be t comma tau, where both are continuous variables. But what we have done is we have discretized just for simplification of and to help us in our understanding. Now I want you to go back in your notes and look at the previous expressions. A very interesting thing, we make an observation. FC is carrier frequency. It is 1 gigahertz or something. It's a very large number. FD, if you did a little calculation, if you did 60 kilometers per hour, you will find that it comes out to be some 100 hertz or 150 hertz. So these two are two very different, in terms of magnitude, they're very different. So one thing that we observe is this theta ends is a very sensitive parameter. Even if the multipath changes slightly, it will make a big difference, because if you are talking about a carrier frequency of 2 gigahertz, the time period at 2 gigahertz is only 0.5 nanoseconds. So if I have a change, if delta tau n changes by 0.5 nanoseconds, theta n will change by 2 pi. That's the carrier frequency, right? Basically one period. So and 0.5 nanoseconds at the speed of light basically corresponds to 0.15 meters. So 15 centimeters is what you need to move at 2 gigahertz to cause a completely different looking channel, which is very similar to what we already observed, that if I move slightly, there is a perturbation of the channel, and therefore the channel conditions are different. So this theta n is something that is very sensitive. Even a small change in the delays of the multipath components can make a big change. On the other hand, fd of n is small, but notice that it has got a dependence on t. That means it will go on changing. It's slow, but it goes on changing. So that is why the channel in a wireless environment, wireless multipath environment, is not a constant. Things are constantly changing, and small perturbations, suddenly there will be a big jump. And so you can see that there is a interplay between these two terms, and again keep in mind the expressions, and that will give us a lot of insight into into our understanding of this system. Okay, so let us move on, and we will come back to explaining more aspects regarding this. So the first point is that we have a time varying channel. Time varying channel, which is denoted by h of t comma tau. Second thing is, don't interpret as don't call this impulse response. Don't interpret as convolution using impulse response. It is tricky. You have to be careful how you implement it. So therefore, I would say that be careful in how you interpret. Okay? It is not. It is a time varying impulse, time varying channel response, but we don't call it impulse response. Okay. So let's look at one. I want to gain some insight. Let's look at some aspects of this particular multipath channel. Okay. I want to look at what happens if my transmitted signal is a sinusoid, a cosine 2 pi fct, just a simple sinusoid with an amplitude A. What is the baseband signal for this? If you have to go back and forth, it is A e power j2 pi fct, and if I basically were to look at remove the e power j2 pi fct, what will I left be with A. So in this case, what is the baseband received signal? This will be A is a constant, summation over n alpha n of t e power j phi n t comma tau, where this is equal to theta n t comma tau t comma tau plus psi n t comma tau. I basically have combined the two terms into a single thing. So this is what gives us a lot of insight, because what is happening here, it is a superposition of phasors. What we get here is a superposition of phasors. Okay, so now there are several interesting insights that you would have already come across when I take this kind of superposition of random phasors which have magnitude and phase angles, and I add them up. Then I get some interesting behaviors in the system, and that is what we want to dwell upon. Okay, so this is a case where I took only complex sinusoids. Now I want to extend it to our understanding of the multipath channel, and it's only it's a single step that is away from here. Okay, so if I were to assume that all the paths, multipath components, arrive at approximately the same time instant. Now first question would be is it really a realistic assumption, because these are going through different paths? Isn't there going to be some difference between the paths that when they arrive? The answer is yes. There will be, of course, even if there's a slight difference in the distance traversed, there will be a difference in the time. But in our processing of these signals, there is something known as time resolvability window. Time resolvability. Okay, I'm sure you have come across this. Supposing there were two vectors that were very, very close in time, but you did not have the ability, your time resolving window was much wider. Okay, basically you cannot differentiate between these two. The resultant signal comes out to be, it looks like something which is just one multipath component, because you are not able to resolve these two. So that is what happens for us also, because the time resolvability window or the resolution, time resolution, is inversely proportional to the bandwidth. The larger the bandwidth of the signal, the more time resolution I will have. But nevertheless, there is always a finite time resolution of the bandwidth. So all we are saying is, when we say that they are coming in the time instant, it is within the time resolvability window, which is a reasonable assumption, because I cannot differentiate it in my processing. So I'm going to make the assumption that all of my tau n of t's are approximately tau, single value. Now please tell me what will be the received signal. R of t will be summation over n alpha n. Notice that the first term, which consists of the carrier component, will now become a constant, because it is all the tau n's are the same, and carrier frequency is the same for fc is the same in all those terms. Then the next term will be e power minus j 2 pi f d n t minus tau, okay, and then of course you will have u of t minus tau. But notice that you can factor out u of t minus tau. You can now see that this is very similar to the superposition of phasors that you saw in the previous example. So what is happening is, for all those multipath components that are arriving approximately at the same time, it is a superposition of random phasors. That is what is the resultant signal. Now we are making the assumption that all the multipaths are arriving within the same. So this whole thing multiplied by u of t minus tau. Okay, so this is what we are interested in. This is going to be the resultant of the signal that I observe. So for this we move into a mathematical formulation, but before that I just want to sort of anchor it in some very good intuition. So there are three things that we have talked about so far. One is path loss. As you move away from the base station, there is a path loss component. That is number one, that is large scale. Another large scale phenomenon that we saw was shadowing. So basically, if there is a building, all of a sudden the signal level will drop, and therefore you have to account for that, and we saw that that could be modeled as a log normal shadowing. So if it was only path loss, it would be some straight line with a path loss exponent as the slope. On top of that, if I have shadowing, in some cases the path loss exponent is the path loss is slightly more, some cases the path loss is slightly less. So there is some variation about the path loss which is caused by the shadowing. So straight line is only the path loss, the solid dashed line are the path loss with the shadowing taken into account. Okay. There is a third element, I am not sure if you can see it on the screen. There is a dashed line, not a bold dashed line, but a normal dashed line superposed on the shadowing effects. That is, there is path loss, there is shadowing, and if I move within a 10 lambda to 20 lambda, within this window, it is not constant, but there is some fluctuation. And that fluctuation depends on what happens with these multipath components and how they are adding constructively or destructively. That is the intent of our. So now we move forward to a model that will help us, a mathematical model that helps us understand what is going on in this phenomenon. So basically we will now derive a model for multipath propagation channel where all the multipath components are arriving within the time resolution window. So we make certain assumptions, simple assumptions which help us to analyze the, so we will say that there are n paths where n is large. What that means is there are different objects in the vicinity that either have reflected or have scattered. So such an environment is called a rich scattering environment. That means there are large number of scatterers present. Okay, large number of scatterers, either reflection or diffraction. So basically there are several objects that are contributing to the resultant signal. Then we also assume that these objects are uniformly distributed in angle. That means these objects are not all in one direction, they are all around the mobile. So you may ask, how can it be if the base station is in this direction, how can there be an object that is in that direction? But basically what we are saying is these scatterers are uniformly distributed around the device. So we will make the assumption that they are uniformly distributed. Okay, all around. They are all around in terms of the angle. In terms of the angle, that means the angle of arrival is not in any is not biased in one direction. The multipath components can arrive pretty much in any of the direction. And the third one, which is very, very important, there is no line of sight component, because if there was a line of sight component, that will be much stronger than the others. So basically there is no line of sight component. Now these are the broad assumptions that we have, and under these assumptions the received signal R of t, complex baseband notation, is summation n equal to 1 through n alpha n e power j phi n t comma tau u of t minus tau. Notice I have dropped the tau n's because all the taus are arriving at the same instant of time. So if I take u of t outside, I get my total gain in terms of the summation of these phasors. Let me call that as some complex variable z. I am doing some very simple manipulations to get the form that we are familiar with. So basically each of these individual components, I am going to write it in terms of the Cartesian components. So there is a xn plus j times yn, basically the real part and imaginary part. So the resultant z can be written as a real part plus j times an imaginary part, where zr is the summation over n is equal to 1 through n of all the xn's, the real components, the real parts, and the imaginary part will be the summation of n equal to 1 through n x of y of n. So what have I done? My net channel gain Z is a summation of phasors. I have done a decomposition of each of the phasors into real part and imaginary part. Then overall Z can be split up into a real part and imaginary part. That gives me two expressions that we have here. Okay. Now, what are some of the assumptions that we have made? We have made that these angles are uniformly distributed. Angle of arrivals are uniformly distributed. Angle of arrival is uniformly distributed. Uniformly distributed. Okay. So the statistical model that we are what we have derived is that ZR and ZI are both superpositions of a large number of identical parameters, because there is no line of sight component. All of these are some multipath component coming in different directions. So by central limit theorem, ZR and ZI will tend to Gaussian, and because we have already made the assumption that n is large, these are Gaussian in terms of their distribution. ZR and ZI are Gaussian. Okay. Now, if I were to think of a angle, basically phi as tan inverse of ZI by ZR, think of it as the resultant ZR and ZI are the real and imaginary parts. Phi is the angle. We can think, by the assumption that we have made, phi can be from any direction. I don't know which direction, Z does not. So phi is uniformly distributed anywhere in 0 to 2 pi, uniformly distributed in the range 0 to 2 pi. Okay. So this is the statistical characterization that we have made. Let me quickly summarize. Whenever all the multipath components are arriving at the same time, the equation that we work with is a superposition of phasors. The phasors can be decomposed into real part and imaginary part. If I have large number of these phasor components, then by central limit theorem, the real part of the resultant channel and the imaginary part both Gaussian. The resultant angle between them is uniformly distributed in terms of the angle of arrival. Now, why is all of this important? Because of the following reason. So basically, if I were to ask you what is mod Z will be a square root of ZR squared plus ZI squared. Okay. Now let me explain why this is important. Because of the following reason. If I were dealing with an AWGN channel, my received signal R of t complex baseband would be U of t plus eta of t, and you have already done some computer experiments where you know how to measure SNR. Now, what will it be if the same signal, same AWGN impairment, but was passing through a fading channel? Okay. What would be the received signal? So in fading, let me use a different color. If this was a fading environment, multipath fading environment where all of them were arriving at the same time, R of t would be equal to Z of t times U of t plus eta of t. What's the impact? The SNR in fading. SNR in a fading environment, let me call it as SNR subscript fading. If I were to ask you, it will be mod Z squared. I am just omitting the t bracket. It will be mod Z squared times the SNR in AWGN. Is that correct? Because it got scaled by a complex factor alpha, which got with a phase term. But what is important for me is the power of the signal. So it will be actually mod Z because I'm taking in amplitude will be mod z, power will be mod z squared. So this is why it is very, very important, because my SNR is no longer a constant, it is now a random variable. And what type of random variable is it? I'm going to ask, we're going to ask the question, so the important thing that we need to get from this discussion is what is the distribution? What is the distribution of mod z? Because that's going to tell me how my signal is going to vary. It's also going to tell me how my SNR is going to. What is the PDF? What is the PDF of mod z or mod z square? If I'm talking about SNR, I would be interested in mod z squared. That will also be a random variable with a distribution. Mod z will also be. So as you can see, our basic model has resulted in a particular resultant received signal where the SNR is no longer constant but is actually going to be something that is going to be fluctuating. Okay. Any questions on what we have said so far? Because what we are trying to work towards is a good understanding of what the multipath environment is going to do to my signal. At a first level, we have found out that it is going to multiply the received signal by a complex value z, which is a statistical quantity. Right, statistical quantity. But I'm interested in taking it further, looking at the distribution of mod z, because we know that the individual components, the real part and imaginary part, are Gaussian, and therefore what is the magnitude, that is the PDF of the magnitude. Any questions? Now this is a problem that you may have already come across in your in probability and statistics, but let me just repeat it just in case someone is not very familiar with this particular result. So we are going to make the following assumption: x and y are independent, identically distributed Gaussian random variables. Gaussian random variables, zero mean, and both of them have got a variance sigma squared. Okay, variance sigma squared. X and y are identical, independent, identical distributed Gaussian random variables with zero mean and variance sigma squared. Now, if I defined a random variable which is v equal to x squared plus y squared, will that be a statistical quantity? Yes. What is the distribution of v? It is called a chi-square. It is called a chi-square distribution with 2 degrees of freedom. 2 degrees of freedom. Okay. But my interest now is v is equal to square root of x squared plus y squared. That's what we are interested in, because I'm interested in knowing what is the amplitude, resultant amplitude of the complex signal. Now this is said to have, just like v is equal to x squared plus y squared has a chi-square distribution, square root of x squared plus y squared is said to have a Rayleigh distribution. So basically the definition is x and y are independent, identically distributed Gaussian random variables, zero mean, variance sigma squared. If I define the variable v in this following fashion, then v has Rayleigh PDF, which is given by fv of v is equal to v by sigma squared e power minus v squared by 2 sigma squared if v is greater than 0, greater than or equal to 0, v less than 0. Because basically we are looking at the magnitude of the resultant vector, so it doesn't make sense to talk about negative values of v. We are only interested in the positive side. So basically the Rayleigh PDF is given by this expression. Now, you may be familiar with it or may not be familiar, but I need you to be comfortable with this result because this is one of the foundational results. So, let me quickly run through the steps. I just need to indicate to you how this PDF expression is obtained and then request you to work on it. If there are any doubts and clarifications, we can do that subsequently. So, the relationship that we have is V is equal to square root of x squared plus y squared. We can think of an angle theta which is tan inverse of y by x. So, you can think of the transformation of variables that is happening is from the Cartesian where we have x comma y, it is going to a polar form where we have amplitude and angle V comma theta, and we know that x and y have got Gaussian IID Gaussian random variables. So, basically the relationship would be x is equal to V cos theta, y is equal to V sin theta. I want to know what is the joint PDF of V of theta. I want to obtain, I want to compute this, right, because once I get the joint PDF, from there I can get from there we can get the marginal PDF. The PDF that we are interested in is a marginal PDF of the joint distribution of V and theta. Basically x and y is the Cartesian form, V and theta is the polar form or the polar form, and I just want to get this representation. Okay. So, when I do this sort of a transformation, again I am assuming that some of these results are familiar to you. What we do is take the joint distribution of x and y, make the appropriate substitutions, and very, very important, we have to multiply it by what is called the Jacobian matrix. Right? I am assuming that you are familiar with this, but let me just give you the expression so that even if you are not very familiar, you can be comfortable with the result. So, the determinant of J, the Jacobian matrix, this is called the Jacobian matrix, always comes when we have to do a transformation of variables. Again, this is something that you would have worked with. This is given by, it's a determinant. Determinant basically has the partial derivatives of the old variables with respect to the new variables. Dou x by dou v, dou y by dou v, dou x by dou theta, dou y by dou theta, and modulus of that. Okay. And again we know that x is equal to V cos theta, y is equal to V sin theta. Please do substitute here, it is a simple result. You will get cos theta sin theta minus V sin theta V cos theta basically gives us resultant of V. So, f of V comma theta is actually a very simple and a compact expression. V of theta is the Jacobian determinant of the Jacobian is V. Then we have the two PDFs, the joint PDFs, but because they are independent, we can write them as a product of their marginal PDFs, fx of x, fy of y. Each of them is a Gaussian. Please substitute the expressions for the Gaussians. What we will get is V divided by 2 pi sigma squared e power minus x squared by y squared by 2 sigma squared. Okay. This is nothing but in terms of the new variables, it will be V divided by 2 pi sigma squared e power minus V squared by 2 sigma squared. I think you can already see the result more or less in front of us. To get the, this is the joint PDF of V comma theta. So, what we need to do is to get the marginal PDF. Fv of V would be, I have to multiply this joint PDF with the and integrate it basically over the range of the other variable theta. So, basically if I do that integral 0 to 2 pi of this quantity times d theta, basically that will come out to be 2 pi. So this will give me V by 2 sigma, V by sigma squared, V by sigma squared e power minus V squared by 2 sigma squared. Okay. So again the key steps: visualizing this as a transformation of variables x and y, treating it as a Cartesian form, V, which is the magnitude, and theta being the angle, as the polar form, the transformation of variables using the Jacobian, and using that from there to get the marginal PDF. Okay. So the expression for the PDF of V, where V is equal to square root of x squared plus y squared, has been obtained, and this is what is called as the Rayleigh PDF. Now the reason we obtain the distribution is because we can work with it. So the first thing, whenever you get, because this variable V is going to affect your amplitude, it is also going to affect your SNR, and it is going to affect outage, it is going to affect many things in terms of your the working of your wireless system. So our ability to work with this is with this statistical framework is extremely important. Okay. So let me just do the following, give you a series of tasks for you to work with. Here are some simple things that I would like you to do. First thing, how do you verify that something is a valid PDF? Integrate it over its entire range and show that it is equal to 1. So first thing I would like you to do is verify that FV of V is a valid PDF. Valid PDF. Okay. So basically what that will entail is you take it from 0 to infinity. V by sigma squared e power minus V squared by 2 sigma squared dV, is this equal to 1? Need you to verify. Okay. Now one of the things that we would very much need as a tool in this course, or this portion of the course, is familiarity with these known integrals. Again, we don't expect you to, some of these are fairly easy, some of them are known standard integrals. Wherever you can use a standard integral, feel free to use it, because the idea is to what is the final result. Okay. Now in this case you can do a simple transformation. Let me give you a hint. Sure, maybe if you have not already seen this, if you do the substitution U is equal to V squared by 2 sigma squared, then you will get a very simple form which comes out to be, gives you the expression that it's equal to 1. So this simple substitution sometimes gives us a good result for us to work with. Now I want to do a couple of things. One is, I need us to understand the properties of the Rayleigh PDF. One, of course, I have verified this. The properties of the Rayleigh PDF is, one is what is the mean, what is the mean squared value, expected value of V squared. Of course, that will give me the standard, the variance and the standard deviation. I would also be interested in the median value. I would be interested in understanding the cumulative distribution function. Again, I will explain why all of these. So there are a series of properties that we want to understand, because Rayleigh distribution is an important one. But before we go into that, let me give you a little bit of insight into what is happening. Okay? Always very important that we get good intuition into what we are working with. So think of the scenario where the electric field is propagating. The signal is propagating in three directions from the base station. One is being completely obstructed by one of the buildings, so nothing propagates beyond that. Another path gets reflected, so therefore you get a certain direction of the electromagnetic wave, and then a third direction that is happening. Now this particular scenario where you just have two of these waves coming in different directions with different phases, when they add together, you will find that there is a peaks and troughs are happening. That's basically interfering, these two signals adding constructively or destructively. Now this phenomenon extended to arbitrary number of multipath components. So then what you have is a very complex set of peaks and troughs, the amplitudes of which, the real part and imaginary part, if you were to represent this in complex, each of them looks Gaussian. If you were to look at the magnitude of the peaks and troughs, the distribution that is happening here, that would be Rayleigh distributed. Okay. So again, what we are doing is mathematical in nature, but keep the underlying physical phenomenon happening, what is happening very much in your picture. Okay. So properties of Rayleigh PDF. So the first property, expected value of V. Okay. Again, all of these are integrals that you need to verify. 0 to infinity V times the PDF of V, which is V by 2 sigma squared e power minus V squared by 2 sigma squared dV. Now many of these integrals are not easy to do because of their form. So what we very commonly use in engineering practice is a book called Gradstein and Rayleigh, table of integrals, series and products. You may have used it in the communications course, and usually their formula, that is formulae that are given using some numbers, right, basically which chapter, which section and all of that. So if you know the indexing of the formula, you can actually come. So basically I have given you two examples of formulae from Gradstein and Rayleigh. It turns out that these two are used in defining the properties. So feel free to use any of these standard integrals, but make sure you interpret them correctly, because Gradstein and Rayleigh has got some notations that we don't come across. For example, in this particular 0 to infinity x of 2n e power minus px squared dx has got something with a double what is this, factorial, double factorial. 2n minus 1 double factorial is only the odd terms, 1, 3, 5, 2n minus 1. It's his notation. Again, whatever is the notation used, please make sure you are understanding that, because it is important that we use these results correctly. Okay. So the result that we would need for our discussion turns out to be one of the results in Gradstein and Rayleigh. Please do substitute the results and verify that this comes out to be sigma root of pi by 2. Again, doing it the long way would be quite cumbersome. Just use the standard results and verify that this is indeed the case. Okay. Now expected value of V squared. Expected value of V squared would be, you expect it to be a slightly more difficult integral, V squared into V divided by 2 sigma squared e power minus V squared by 2 sigma squared dV. Again, we would have to use our Gradstein and Rayleigh and look for suitable formulae, or you may know that expected value of V squared is V is equal to x plus Iy, right. This would be V squared would be equal to x squared plus y squared, or let me not confuse you. We defined V as square root of x squared plus y squared. So V squared will be x squared plus y squared. So expected value of V squared will be expected value of x squared plus y squared, each of these. So you can write down without even doing any calculation, it should be 2 sigma squared, because each of those has got variance sigma squared. The x and y, both of them individually have got, but of course what I would like you to do is also be able to do it using the integration method. Let me give you a hint for this also. X is equal to V squared by 2 sigma squared. Please do the substitution, it will come out to be a very simple integral. You will have to do integration by parts, but it's still a easy enough integral that you can work with. Integration by parts, and please verify that the answer must come out to be 2 sigma squared. That's the correct answer. Okay, so let me give you one more insight, which I will repeat again in the next lecture. But what I want you to think about is the following. When we have the small scale fading, what the path loss and the shadowing tells me is what is the RMS, what is the level that average level that I will receive. Okay, I'll call it VRMS. So that is the signal level. Now about that level, I am going to see fluctuations, fast fluctuations based on my position. I move a little bit, suddenly there's a dip. If I move again, there's a, so this is a very, very tricky phenomenon that I need to worry about. So one of the things that we are going to ask is how much margin, you know that how much margin you should keep for shadowing, because we know that's going to result in outage. Now in addition to the margin that you have kept for shadowing, you must keep some margin for this fast fading, otherwise the fast fading will cause you to go into outage. So one of the things that we are, one of the reasons why we are so interested in saying what is the expected value, what is the expected value of V, what is the expected value of V squared, all of these properties is because I want to know how much margin I should have for fast fading. Okay, it's an important element in our understanding of the small scale effects. It is also important in our design of our system so that we get a good and efficient design of the system that will work in the presence of path loss, in the presence of shadowing, and in the presence of multipath fading. Okay, this is where I will end, but this is a figure that we're going to come back to do it. Please make sure that you are able to just verify the PDF, the properties of the PDF. Again, we will build on that in the next lecture.